Hi, everybody. I see many familiar returnees. You're seeing me again. I'm spending a lot of time with many of you today. For those of you who are just joining us for this session, thank you for joining us for Lamont Open House at Home, our first ever virtual open house. And this particular session, Laurel Zaima is going to be teaching us about, we're continuing ice today. We have lots of ice related things going on. Our scientists do a lot of work at the poles. And Laurel today, Laurel is our education and outreach coordinator at Lamont, and she is going to be sharing with us how you make glacier goo. And she's going to talk a little bit about how ice actually flows. And it doesn't just sit there like we think that it does. And she's going to show us how to actually make it. And you'll see that on her screen, she's got all the materials and supplies ready to go. For those of you who are just joining us, I just wanted to tell you a little bit about the open house tradition at Lamont. So Lamont Doherty Earth Observatory, we're located in Palisades, New York, and we have been doing open house for more than 50 years. We were founded and created in 1949, and the first director of Lamont, Marie Stock Ewing, decided that he really wanted to open up our science campus to the community one day a year. And so usually open house is held on our campus in Palisades, New York, and every lab is open, every scientist and staff member participates, and it's just a fantastic opportunity to learn a little bit more about the science that we do. But this year, we've miraculously moved all of that online. And we're so glad that we can actually be reaching new audiences. So even if you're not based in New York, you physically can't be at a future open house, I think this year is a fantastic opportunity to tune in to some of our sessions. We started yesterday, and virtual open house is going to go until Thursday. So you have plenty of opportunities. Everything is being recorded. Everything is going to be posted to our YouTube video page, and you can continue to engage throughout the week. So I will turn it over to Laurel. Just a quick note, we are going to be using the Q&A box today. So if you do have questions throughout, definitely type it in there. Laurel, I will probably wait towards the end of your sort of demo and talk, but if there's a specific question about something you're doing with the recipe, I'll definitely let you know. For those of you who may not have received the recipe, so we can, I'll share the recipe again. I believe we can also share it online. Many of you have signed up for our LDO to go packet, which does include a recipe, the Glacier Goo recipe. If you haven't, I'll put the link to sign up for that packet. We just have a few left. I'll put the link in that packet in the chat box, and we can definitely mail you a packet. But if not, we will definitely share the detailed items that you'll need. Okay, Laurel, take it away. Thank you.
Hi, everyone. As Cassie said, my name is Laurel Zaima. I'm the Education and Outreach Coordinator at Lamont, and I have the pleasure of working with the scientists that get to study these polar regions. So the Arctic at the top of the world and Antarctic at the bottom. They're called polar geophysicists. And so every year at Open House, we create Glacier Goo to help explain glacier physics to anyone who wants to stop by our tent. And so I'm going to do that today. I'm also going to show you how we make Glacier Goo. It's pretty easy, as you guys can see in this other view over here. It's a lot of household items that you might already have, which is great. I'm going to walk you through step by step, and if you have any questions, feel free to let me know. I'm going to stop that video now, and now we're going to focus on the making of Glacier Goo. So the first thing you want to do is you want to get the Elmer's washable white glue. This is what we found works the best. Anything with like sparkles in it can work. This Glacier Goo recipe is also similar to a slime recipe if you're familiar with that. The first thing you want to do is measure out 1 cup of Elmer's glue. So I'm going to do that now. This is a a great step that you can do with students or children at home. Working with the glue is always fun. So we're just about at a cup there. Perfect. So pour that cup into a larger mixing bowl that you're going to be using to dilute this glue. That's our first step. So I'm just going to scrape out the first cup, and then we are going to add 3/4 cup of warm water that I have over here. And you basically are diluting the Elmer's glue. So that's 1 cup, or 1/4, 2/4, and 3/4. And then you just want to make sure you're stirring up this mixture until it is completely blended together. Just changing the viscosity of the glue, making it a little bit more runny. And this will just take a couple seconds. And we're going to be making 2 mixtures separately and then combining them together. So this is mixture 1. All right, we're actually in pretty good shape here. So as you can see, the glue just has a more liquidy viscosity. And that's really what you're looking for there. Perfect. Okay. Let's set that aside. And then in your second mixture, you want to measure out a 1/2 cup of warm water. I already measured it out here. It's nice and warm. And this is going to be creating your borax mixture. So borax can be found at any store if you don't have it, or you can order it online. You just want to be careful with this step with children because borax is toxic to inhale or ingest. So I would make sure that an adult is handling this step. You're going to use 2 teaspoons of borax. So I actually pre-measured this out just for the sake of time. So this is 2 teaspoons right here. And we are going to just pour it into this warm water mixture and dissolve. So then you're just gonna stir this up until completely dissolved into this solution. And this shouldn't take too long, especially if your water is nice and warm. So should look something like that. All right, this is the fun part. So now that we have our 2 mixtures, you're going to be adding this borax mixture into, needs a little bit more stirring, but you're gonna add this borax mixture right into your glue mixture.
Laurel, before we continue, we just had a quick question about how much water with the borax.
Oh, yes.
A quick clarification. It was 1/2 cup?
Yes.
Okay, thank you.
Perfect. 1/2 cup and then 2 teaspoons of borax. Okay, now we're combining these 2 mixtures, and the moment you do this, it's gonna start forming globs. So you're gonna wanna have one person stirring or multitask and pour it right in. Here we go, and you can already see the globs are starting to form. You're going to mix for about 2 to 3 minutes, and then you're gonna start kneading with your hands. So as you can see, this just globbed up right away. And one thing you do want to be careful of, I've definitely made this mistake in the past, if you use too much borax, your substance is going to be too hard and it won't work for the glacier physics because it won't flow properly. So if you find that your glacier goo is a little bit too stiff, it's not flowing properly, then too much borax, you can just start again. Okay, pretty globby in here. So I'm going to switch over from the spoon to my hands and just start kneading it together. And it's gonna be a little liquidy at the moment. And when you're finished with your glacier goo, it's okay if there's a little bit of leftover water. You can just drain that bit and then let your glacier goo harden on the side for a little. So this is pretty much it. It's really simple to do. Here's our glacier goo. It needs to sit a little bit, I would say, like rest. But I did make a batch earlier today so we can jump into our glacier physics if if everyone's ready. Unless anyone has any questions about how to make glacier goo before we keep going.
I think we're good.
Okay, it's
Yeah.
gonna be a little slimy.
Yeah.
But that's okay. We're all about having fun and making messes. Okay, I'm going to shift everyone over to our little physics station here. There we go. Okay, so as I mentioned, I created a batch earlier today, and this is what the end product is going to be after it rests for a little bit and you drain that water. It is able to come together a little bit more easily, but if you want, you can also break it apart into smaller bits. So for our experiments, I actually just created a smaller ball that we're going to be using. Okay. Also going to turn this around so you guys can also see me doing the experiments. With the first one we're going to look at is how gravity impacts glaciers. So the first thing we're going to do is ball up your glacier goo, and you're going to put it down on a piece of paper that has, you can use a laminated piece of paper if you have a laminator. If you don't, like I don't, I just put it in a Ziploc bag. You could also use saran wrap, really whatever you have at home that you're able to use washable marker on would work great. So now we're going to watch how gravity impacts glacier flow. Now I want everyone at home to make a hypothesis. We're going to ball up our glacier and draw a circle around it. And you guys make a hypothesis. Do you think the glacier is going to stay within the circle, or is it going to go outside of that circle? And while we're waiting for our experiment to run, I just wanted to, something that you would discuss with your students at home, just talking about what gravity is, that it's this force of attraction between two objects, that it's really pulling down an object toward the earth. And so we know that gravity plays a role on bringing an object from the highest point to the lowest point, but even on flat surfaces, it's still going to try and pull that subject, especially if it's malleable, from its highest point to its lowest point. And so as we've been talking about, glaciers, well, they're made out of ice, and we oftentimes think of ice as being solid. When glaciers are this massive, they can flow under the weight of themselves due to gravity, and they flow really slow, kind of like honey. And actually, glaciers get the name rivers of ice because they flow so slowly. And so even though we have this piece of ice, our glacier goo, on a flat surface, you guys can already see that it has started to flatten out and extend beyond the circle that we had initially drawn. So it's just showing how gravity can play a role in malleable objects, not just things that are going from the highest to the lowest point in terms of a hill. So gravity playing a role in our glaciers. That's our first experiment. It's okay if there's any marker, you can just kind of blend it in. The next experiment we're going to be looking at will use some sort of ramp. So in the case of anything you have at home, you could use a board put into a Tupperware container just to create a ramped surface. I actually have a computer ramp, so I'm just going to use this because it's a little bit easier. So I'm going to put my piece of Ziploc start-stop on our ramp here. And the next thing we're going to be looking at is friction, specifically basal friction. So basal means that bottom layer of something, and friction is occurring between two surfaces when they're rubbing against each other. So we're going to next ball up our glacier goo, put it at the top of your ramp, and then we're going to take a toothpick or a matchstick, really anything that you have in your house, and you're going to put it directly in the center of your glacier until it hits the bottom, and we're going to make a hypothesis. Do you think the bottom of the glacier is moving faster than the top of the glacier, which in case would make the toothpick go upward? Or do you think the bottom is moving slower than the top, which would then make the toothpick go downward. So as we're waiting for our experiment to run, if you think about it this way, if we have a ramp and the middle or the bottom is flowing slower than the top, then we're gonna have this tilting of this way. But if we have our top moving faster than our bottom, or our bottom moving faster than the top, then it's going to be tilting upward. Okay, we already have some movement here, but I'm realizing that it's going to be hard for you guys to see this side. So we're going to, so you can see the toothpick is starting to tilt downward, which is saying that the top is moving faster than the bottom. And if you, think about basal friction, the bottom of the glacier is interacting with the bedrock. So it's going to be slowing down the bottom, whereas the faster part of the glacier is going to be moving on the top, which is causing this toothpick to tilt downward. Perfect. All right. Any questions about these two glacier physics experiments that we've done so far? And if not, we can go on to our third experiment, looking at friction again, but in a different way. So, oftentimes glaciers have these channels where the ice is flowing through them. So this is representing our channel here. It's just tin foil. You can wrap it and mold it into different shapes. So I have the top of this channel bulbular, so it will hold the ice. And then it's going to kind of narrow in the center. And we are going to see how friction plays a role on the ice from this channel here. We're going to tape that down. Okay. So once you've created your channel, you're going to take your glacier and ball it up again. And we are going to observe how the channel friction impacts the glacier as it flows. So if you think that we're gonna draw a line with a washable marker straight across this glacier, and if you think the sides are moving faster than the middle, then it's going to form a frowny face. However, if we think the sides are going to flow slower than the middle, it's going to cause a smiley face. So, smiley face or frowny face, you guys can make your hypothesis, and we're going to observe what happens. So, this is frequently something that we see in nature. Oftentimes, if you see real-world photos of glaciers, they're kind of being channeled, or they can even carve their own channels through the rock because they are so heavy and massive. And that interaction between the ice and these channels absolutely impacts on how it's going to flow. All right, and actually you guys can already see.
We have some answers about frowny or smiley face. And we think
perfect.
I think it's smiley.
Smiley face. I completely agree. And you guys can already start to see this happening. So as the smiley face, I see the comments coming in now. So as you see, the middle part is moving faster because the sides are impacted by the friction of the channel. So we're going to be creating this smiley. And oftentimes in real life, we see glaciers that continue this middle moving faster that creates these ice tongues. It's this pretty amazing phenomena. All right. On to our next experiment. We are going to be looking at drag. So we can get rid of our channel here. We're going to ball up our glacier goo, and we are going to see how an object that would be impacting the glacier in an opposite force will change the flow. I just need to find, there it is. Okay, so for my drag, you can use anything that you have at home. You can use a small block. You could use, I'm using a matchbox, really anything that's small enough to be taped onto this flat surface here. So I'm going to tape my object that's imposing drag onto our ramp at the starting point. We have our balled up glacier here, and we're going to put the glacier at the start of this object and see how it is impacted by this piece causing drag. Okay.
Laurel, I have a quick question before we move on to, we had one comment from a viewer that their goo ended up frowning and not smiling. So in this experiment, do you think any ideas on what might have happened?
Did you create the channel so it's hugging the glacier, so it's causing that friction on the sides? If it wasn't, then I don't, yeah, then it might have caused a different shape, but yeah, so the key is that the sides of the channel are actually touching and impacted by this glacier.
Okay. Maybe we can go back after you're done this and maybe just show it again and we can try it again.
Yeah, that sounds great. Okay, so looking at this piece of drag, and just something that you can explain with your students, that drag is a type of friction that's causing a force opposite to this moving object. So it's basically impeding this motion. And it can happen between two fluids or a solid and a fluid. And I know that ice, we think of it as a solid, but again, because it's flowing, we are considering it as a fluid here. And so we're actually already seeing that this piece of this object, it could be a giant rock or a change in landscape. It's really causing the glacier to start to move around it. So it's going to impede the motion in the center, and the glacier is going to continue its movements where there is, it's a free landscape to continue moving. So I would love to also, maybe at the end, I can show you pictures of some of these glacier physics in real life, because it's so crazy to see it as glacier goo and then relate it right back to some of these images that we have. It's pretty cool. Okay, our last experiment. So we're going to take off our piece of drag, our object imposing drag, and now we're going to be looking at force. So again, after every experiment, it's important to ball up your glacier so it starts from a rounded state, and it also kind of heats it up. If your glacier goo gets too cold, it doesn't really flow as fast. So that's just a little trick. So in looking at force, we need to create some sort of push-pull with an object. And so I'm going to hold this box of markers at the starting point, and see how it impacts the flow of ice. So we have our glacier here. I'm going to put it, and in case you guys couldn't see, I have on my board, I have a start and stop approximately 10 centimeters from each other. So you could also even time how long it takes for your glacier to flow 10 centimeter distance and compare it to the flow of other glaciers. So that's a fun activity that we have that we can share. Okay, so we have this force that's imposing a push on this object that's trying to flow down, and we're going to see just how that impacts this glacier. And the reason why this is important is because we have something called an ice shelf that imposes the same type of force. So an ice shelf is this floating platform that's connected to the land on one side and then kind of floats out into the ocean on the other end. So you can think of it, it kind of looks like a shelf. And ice shelves are so important because they create this backstop pressure for glaciers, so they don't continuously flow at fast speeds. So it slows down the flow of glaciers. So let's say our ice shelf breaks off. Now we don't have this force anymore, and our glaciers can start shedding off ice faster. And glaciers, it's natural for them to flow and deposit ice, but the important thing is that they're in balance. So if they have an equilibrium of snow that's contributing toward the glacier and forming into ice, and in equilibrium with the amount of ice that's being flowed out into the ocean, then that glacier is stable. However, if you have an imbalance, whether it's too much snow or not enough snow, then you could have an imbalance where the ice sheet is going to advance with more snow or retreat if there's more melting. Okay, and if you see, perfect, this force is kind of holding back the glacier from flowing just as an ice shelf would. But let's say our ice shelf broke off. Now you're going to watch how the glacier interacts without this force. It's going to continue flowing down at a much faster rate. So this one is really important. This is something that scientists are studying right now and looking at some of the vulnerability of these areas if the ice shelves are broken off and lost. And now you can kind of see it starting to flow down here. All right. Any questions on any of these? We can definitely go back and do the smiley face one if we don't want to do that.
I think another viewer had said perhaps if the incline was in a different direction, that could also affect the way in which it flowed.
Oh yeah, so it depends on where you're standing. If you want to make sure if you're standing below the incline, then it should create that smiley face.
So I think if you want to do that one again, but perhaps show us just from the side which way your incline on that or decline, I guess, is going, so we can see it from the side. That might be helpful.
Yeah, I can definitely do that. So you guys can see my computer stand is inclining, or it's declining toward me, inclining away. So I'm looking at it as it's flowing down.
Okay, great. Okay.
That's an important one. I'm glad someone said that. Okay, so back with our channels. You can really create also anything. I just found that this tinfoil works pretty well. Okay. Kind of creating this shape. Again, where it's like the narrowing of the channel in the bulbular part is where you can just rest your glacier goo. So balling it up, let's put it in. Oops. There we go. I might have made it a little too narrow. And now we're going to draw our line. Straight across. There we go. And we're just going to see how it flows.
Great. Can you turn your camera? We're looking at I guess a portrait view. Yes, perfect. Thank you.
There we go.
Yeah, excellent. Thank you. Would you recommend, while we're waiting for the face to appear, to put this in the fridge if you wanted to keep it for a longer period of time? How do you store it to come back with it? I know you had a batch ready to go, but if you did this, and then would you leave it in the fridge or just sitting at room temperature for a few hours and then coming back to it?
Yeah, that's a good question. I have never put my glacier goo in the fridge. I assume that would keep it longer. However, if you have it in a plastic bag and keep it at room temperature, it will last for months. So I even had a batch in my closet from this past spring during Earth Day, and it was not too bad. Could have worked with it, but I wanted to do a fresh batch just for you guys.
Awesome, thank you. There, I see the
yeah, and you can see this like ice tongue forming as well. So that's a really good point, making sure that you're standing at the bottom of the decline here to see that smiley face. But it's all about how it's interplaying with friction, right? So if you're explaining to students the reason for it, of course, if it's having an interaction with the sides, that rubbing is going to slow down the sides, and the middle that's not impacted by that friction is going to move faster.
Great. So far we don't have any questions. If you do have questions, let us know. Laurel, perhaps if you want to show us a couple of, I guess, real life, the photos of real ice flowing.
Yeah. Okay. Let's see. We have a really amazing packet all set up with the instructions on how to make glacier goo, and each one of these, we call them Bergy Bits activities that we can share at the end as well. So you can pop it right into your classroom or do it at home. All right. First, I'll share my screen. Okay. So for example, this is the first experiment that we did looking at gravity. So it also shows you how to set up your experiment if you forget after we leave here today. And then these are some pictures of real life glaciers, and you can see the flow of them and just how beautiful they are. And I know a lot of people think that glaciers are these remote features that are so distant and kind of unrelated to us, but we actually have glaciers on every continent in the world except for Australia. So they're closer than you think, and they do impact us every day. They have huge implications for sea level rise. That's why it's so important to study how fast they're flowing and whether they're in that equilibrium balance that we talked about earlier. If we have all of this ice that's on land and it's melting and flowing into the ocean, then we're going to have global sea level rise. And so it's so critical to focus on a lot of these hotspot glaciers, and that's what the scientists I work with are looking at as well. This was the second activity that we looked at. So looking at basal friction, again, just reminding everyone that basal means the bottom or the base layer. So that base interacting with the bedrock and how it's going to slow down the bottom as opposed to the top that's going to be moving faster, causing that toothpick to fall. That doesn't have a real life image with it, but this one does. So this was the smiley face that I was talking about, that it's just so cool to see this ice carving out its own path through this landscape, and kind of these channels are slowing down the sides, creating this cool looking ice tongue here. So it really doesn't look too different from the experiments that we're doing, which is kind of fun as well.
So Laurel, we have some questions here. The first question is about the friction on the bottom of a glacier. Does it make heat? I guess like when you rub your hands together and you create friction, and that makes heat. And do you know if that contributes to, if there is heat, does that actually impact melting of the glacier?
Oh, that's interesting. I wouldn't think that there's, because it's moving so slow, I wouldn't think that there's much heat generated. However, that interplay with what the bedrock is and what the surface of the ice sheet is impacting its flow is something that a lot of our scientists are looking at. So if you think about, if there's, let's say, like a layer of melting in between the bedrock and the ice, it's going to increase the speed of that glacier flowing as well. So these like pools of water that are right in between those two layers can actually speed up the flow. So that's a really good question.
Great. And our other question, out of curiosity, why are there no glaciers in Australia?
It is a pretty warm climate, and they don't have high elevation to have any areas of permanent ice.
Great, thank you.
Yeah. This is a cool image of the drag. So looking at a real life landscape change that's causing this ice to flow around it. Kind of all just puts it in perspective. And then this is an example of an ice shelf, just to close it all together.
Perfect. So we have some, so two questions. How does the goo feel in your hand?
That's a great question. It is, once it's finished, it's not as slimy anymore. Like when I was kneading it, it was very slimy. Now it's just kind of squishy and and a little bit wet. But yeah, it's fun. You guys should make it at home.
Someone said it might be like dough.
Yes, like a little bit more. It's so hard to explain the consistency of slime, but a little bit more slimy than dough is.
And then the other question was, how long have you been working at Lamont?
Oh, I've been working at Lamont for 2 years. Um, my background is actually marine biology, but I've been doing education for 4 years now. And so, yeah, I love being at Lamont and learning from all these scientists, and I get to learn new things all the time and then teach you guys about it. So it's great.
Fantastic. Yeah, so any other questions for Laurel? I think the goo is fantastic. It's such a great learning tool, super easy to make. And oh, we have, so Nathan, thank you. His mom is also working at Lamont for 2 years. Yeah, Nathan, I think your mom's name is Anita, right? I'm guessing because she works at IRI. Cool. Glad to see some IRI folks and families and communities. Yeah, I think the goo is so fun. I always love touching it. It doesn't leave anything sticky on your hands, which is what I always am surprised about. Because when you were kneading it, it was like, oh my gosh, that looks like, she's mixing, flour and water. Yeah, yeah. And we have a question about whether or not you've ever gone to Antarctica.
Oh, no, I have not. Most of my colleagues have, and I get to live through their pictures, but maybe one day I'll get to go.
Yeah. And we have a question about the reaction between the borax and the glue. Like how does it react and to kind of form, I guess, the goo?
Yeah, that's a good question. I'm not a chemist, so I can't go into much detail about the chemistry of why this is happening. But that brings up a really good point. Because borax can be a little bit tricky to work with young students in terms of, like, you don't want to inhale it, you don't want to ingest it. Mostly adults would want to handle that step, but there is an alternative method of creating goo and using contact solution, because it has boric acid, which comes from borax, and it will create the same type of effect, but it's safer. So for anyone who is looking for an alternative, there are recipes online that use slime with contact solution instead.
Okay, great. And have you ever wondered what the glaciers felt or looked like in person?
Yes, I would imagine that they feel cold, and the images are incredible, but I'm sure it doesn't do it justice when you're standing at the base of these massive glaciers. So I've definitely wondered that myself. One day, hopefully, I can see one.
Yeah. So I would say that just to add on onto this, you don't have to go to Antarctica to see a glacier. So there's some of the photos that Laurel shows you were from Alaska, I believe, and then there are also parts of Canada. Definitely do not go to Australia to look for glaciers, but I believe there are glacier fields in Jasper, Canada. I think I actually remember going as a kid. Obviously not as dramatic, but just not as dramatic as being in Antarctica. But there, you don't, maybe for the next time that we travel again, we can all go to Canada and look at glaciers. You don't have to go as far as Antarctica, as we've learned over the past couple of days with the open house sessions. Antarctica is really far and hard to get to. And so we are in Alaska, there's glaciers. And then if you are also ever lucky enough to get up to Greenland, there's also glaciers up in the Arctic, right? Great. Any last questions for Laurel? If you have, we have one question here. Can rocks get caught in glaciers?
Yes, that is a wonderful question. Because glaciers are so heavy and massive and they're moving, they can actually carry rocks with them. And at the base of the glacier or at the extent of the glacier, if it starts to retreat back, so let's say there's melting, it will deposit these rocks into something that's called a moraine. So oftentimes we look at moraines, we're looking at what the extent of that glacier was in the past. And a fun example of a moraine is actually Long Island. So Long Island was formed from a moving glacier back in the Ice Age when the Laurentide ice sheet covered the northern part of the United States and into Canada. It formed that Long Island from a moraine.
And I'll add that I think this was touched on briefly in a presentation yesterday, but scientists also study ice cores, and they don't see rocks, but they definitely, if you can pull out an ice core from sort of a very thick sheet of ice, you do end up seeing dust particles, and based on those dust particles, you can gauge, also you can get a lot of information from them. So things definitely do get trapped in the ice. And then we have a question about what's, I guess, the coldest place you've ever been to that might be similar to Antarctica. So Indrani presented before this, and she had said, there's two types of weather in Antarctica: cold and colder. So yeah, so I'm curious what the coldest place you've been to has been.
That's a good question. So I actually have been to Alaska, but I was so young when I saw Glacier and I was in Alaska that I don't really remember it. But I do remember it being painfully cold, and we went in the summertime. So I don't know what that says, if that means that I'm not very good, I'm not tolerant of the cold weather, or if it means that that was the coldest place I've been to, but it was an amazing experience. Yeah, I'd love to go back as an adult.
Great, fantastic. Cool. So I think we have our questions done. If anybody has any additional questions about the goo, also if you are looking for the recipe for the goo or you'd like a packet, please email me. I put in the link to get the LDO to go packet, and I'll just share that again in the, whoops, wrong. Oh my gosh, I copied something else here. So let's try that again. I'm going to redo this. So if you do have questions for me, though, you can definitely reach out, and Laurel will be happy to answer additional questions. And we have 2 more days of open house. So there it is again with the link to get your Glacier Goo recipe. Laurel, if you any last sort of comments from you, I'm going to type in my email address for everybody. So if you do have questions for Laurel or myself, let us know. And we have, like I said, we have 2 more days of open house. And Laurel is actually going to be back tomorrow to talk about the Hudson River Field Station. And we can learn more about the Hudson River estuary and fish, the amazing creatures that live in the Hudson.
Yes. So definitely join us tomorrow for that. The last thing I just want to say about glaciers is that they're this incredible feature that do have huge implications for us, and we are connected to these glaciers, that we're causing changes to these glaciers through climate change, and that is a key thing that our scientists are studying, is how these glaciers are changing. And so we want to make sure that anything that we can do in our lives to lower our carbon footprint, to be positive environmental stewards is so critical, and it does make a difference. So even if it means everyone watching today, go home and tell all your friends and family about what you learned and why glaciers are so important, that will make a huge difference.
Great. Great message for all of us to take away. So yeah, thank you, Laurel, and thank you so much, everybody, for your time. Contact us and let us know if you have any questions, and hope you make some goo. And if you do, share the photos with us. You can tag hashtag LDEO to go, or you can hashtag I think it's I got a open house at, or no, it's hashtag Lamont Rocks. There's a lot of hashtags out there. So, but send us a photo if you end up making goo and playing around with it. And we hope that you tune in for future sessions. So thank you so much for your time, Laurel, and thank you, everybody, and hope you have a great rest of your day.
Of course. Thanks, everybody.
Bye.